Any doubt from last class? Do you have any doubt from last class?
No, sir.
Okay. So we had completed till stress strain curve. The next and this last part is potential energy stored in a wire. Suppose there is a wire attached from any support like this. On application of force along this direction or deforming force along this direction, F, this wire may get stressed by some amount to do this part. But this deformation produced in this wire must have achieved in stepwise. So total deformation from this point to this point is small l. Actual length of wire from this point to this point is capital N, and area of cross section is A. So consider a wire having dimension A cross L on which a deforming force is applied F. So we can define first about this F. Let's suppose this particular deformation total small l may have achieved in stepwise. So initially it will be from this point to this point, then till this point, and then till this point. So in last step, from this point to this point, I'm taking as dy, and rest of the term from this point to this point, let's say y. Is it clear?
Yes, sir.
Abdul Wahid, any doubt? So according to relation, Young's modulus equals to stress by strain. Stress is F by A. Strain is deformation produced divided by its original length. Let deformation is Y and original length of object is L. So you will get F equals to Y into A divided by L into small y. Now, to stretch it further by dy, a small work must be applied on this to stretch it by dy. So let's say let dw amount of work is done to stretch it by dy. This work will transform or convert it into potential energy. So this will get stored as potential energy. So work done is equals to force times displacement. Force is YA divided by L into Y dy equals to work done. On integrating both sides, integration of this work done will be total potential energy. Since Y, A, and L is constant, so keep it outside. This small y having exponential 1, so using formula of integration, it will be y squared divided by 2 and limit extending from 0 to maximum small. So you will get y squared divided by 2 limit from 0 to n. Ya divided by L into 2. Put the value of y first to the upper limit. So it will be L square, and lower limit, it will be 0 square. On simplifying, you will get half YAL times L square is equals to potential energy stored. We may rearrange this equation as half times Y into A divided by L into small l first and then small l. This whole term will behave as force and this term will be extension. So you may write it as half times force times extension is equals to potential energy stored. Is it clear?
Yes, sir.
Okay, just write it down.
Done.
Abdul Wahid, you have written? Okay. Now, since force and extension are in multiplication, so you may write it as area under force extension graph will define you potential energy stored in this wire. Now we may transform this formula like U is equals to half into force into extension. Now, if we divide this whole term by volume, divide by volume, multiplied by volume. So there will be no change in this particular fraction. So we may write it as half force into extension. Volume is area into length multiplied by volume. This term is nothing but stress. This term is nothing but strain. So we will say it will be half into stress into strain into volume is equals to potential energy stored. Is it clear?
Yes, sir.
Wahid, any doubt? You all have written to this?
Yes, sir.
Shwab, any doubt? Now, there are some term related in this particular chapter. First is elastomer. You must have used thermocol for some project and for some other use. If you compress that thermocol up to a small displacement or up to a small compression and release it, it will come to its original state initially as it was. But if you further compress it a little bit more, it will get fractured or broken up. So you will say a substance which having only elastic limit beyond which it get fractured are termed as elastic limit or elastomer. Is it clear?
Yes, sir.
So suppose this is amount of stress, elastomer, ELASTOMER, corresponding amount of strain developed. So graph of these type of material will be like this. While elongation and while compression. So the maximum limit up to which there will be no breaking is termed as saturation point, beyond which it will get fractured. So it will be the substance which has only elastic limit. And beyond which it will get fractured. It will be termed as elastomer. Now, mechanically, it will be used for shock absorber. So you'll say, greater the area of this particular curve for that substance, it will have ability to absorb more amount of shock, or it will dissipate more amount of energy while jerking or anything. So you'll say it is used as shock absorber the greater the area of curve. So it will be good shock absorber. Is it clear?
Yes, sir.
Wahid, any doubt? Yes. Shock absorber, to absorb shock, not observer. Observer is any individual which observe some situation or experiment. You all have written?
Yes, sir.
Okay. There is one another term that is called Poisson's ratio. Suppose you have a solid like this, which having actual length from this point to this point, and actual diameter is this much or width. If you apply any deforming force on it, so on elongation, width of this rod must get decreased. So it will be like this. So this is amount of elongation produced in this, let's say delta L. Correspondingly, there will be change in its diameter. Initially, it was from this point to this point, and now it gets reduced to this point. So this will be d minus delta d. Is it clear?
Yes.
So we have two different deformation. First is in terms of length. So it will be termed as longitudinal strain. So it will be delta L divided by L. Second is in terms of its width, which is called lateral strain. So it will be delta D divided by D or delta R divided by R in terms of diameter or in terms of radius. Since this particular width is decreasing, so there will be negative sign and negative sign here. Is it clear?
Yeah.
So the ratio of these two deformations produced in this particular solid is called Poisson's ratio, which is denoted by sigma. So it will be lateral strain divided by longitudinal strain, or you may write it as delta D divided by D, delta L divided by L with negative sign. So you'll say both in numerator and denominator is strain, which is unitless quantity. So sigma or Poisson's ratio will be unitless quantity. For rigid body, sigma equals to 0.5. There are some theoretical value and experimental value related to this part. Sigma lie from 0 to less than 0.4, minus 1 to less than 0.5. This is practical value and this is theoretical value. So you have to remember only this term. You may be asked to define value of Poisson's ratio for perfectly rigid body. So it will be just 0.5. Is it clear?
Yes.
Abdul Wahid, any doubt?